Good morning, ladies and gentlemen. So my name is Fabien Rezeber, in charge of marketing at Performance Polymer EMEA at Mitsubishi Chemical Group in Europe then. First of all, I would like to apologize for not being able to be with you all in Rennes today. I had to make this presentation remotely, and for this I would like to thank Pauline and the organization to still allow us to do that remotely today. The presentation will be about innovative compound that we are developing and that we have developed for some of them for electronics today. So that will be involved in communication topic and also about conductivity properties. So as my colleague Nathalie Lepré explained to you probably yesterday when you introduced all the booths, we are Mitsubishi Chemical Group. We are a 30 billion revenue company, a global one, a Japanese one with almost 70,000 employees over the world. We are a major chemical company, of course, with a lot of very different solutions. We are also operating on a lot of different markets, like the one described here on the screen, like EV mobility, digital, food, medical, construction, consumer, and industrial goods. Actually, we are not only a supplier of plastic materials. As you may know or recognize here, we are also able to supply battery solutions, composites, semiconductors, goods, and services to clean them. A lot of barrier material, food additives for food additives, yes, chemical foods additives. We have also industrial shapes in plastic that could be then shapes to make the final parts. So it's a lot of very different material that we can provide for all these applications, and we decided to focus on this market because we do believe they are the one that will be key for people in the future, and we have solutions that can help this market to grow on a more sustainable way. Coming to MCPP, so PP stands for Performance Polymer because we are a global supplier of performance polymers, meaning compounds, specialty compounds, that are most of the time customized specifically for our customers. I will not describe all the portfolio here, but as we are mainly dealing with mobility in this conference, for sure you may recognize some brands that we have here, like Olefista, that is halogen-free compounds that are flame retarded without any halogen, that can be used widely in automotive industry. We have Marviflow, that is a PVC compound powder that is mainly used for slush molding application, and in mobility we are making dashboards and different kind of interior parts with this kind of solution. And probably the main product we are selling in Europe nowadays, so Tefabloc and Thermoren, they are thermoplastic elastomers. So Tefabloc is mainly based on styrenic elastomers for a lot of very different applications, not only in mobility. Thermoren is only for mobility, and this is the specific brand of material we have for making airbag covers. So we are one of the leaders in Europe for airbag covers. Just behind my picture here, we have also Trexpren, that is TPV compound, but it's not a range of product that we are distributing so much in Europe nowadays. So for this presentation today, the idea is to show you also what kind of development we are making in pioneer applications, or what kind of new functionality we try to provide for our compounds in electronics. So this presentation will be mainly about working on conductivity material, but we're also working with fire retardancy systems, working on the lightweight, working on the acoustic systems as well. All of the time we need also to work on sustainable way, so we are considering the sustainability topic as one of the key drivers for development for within our R&D. And as mentioned to you today, I will focus mainly on this kind of topic today. So what about sustainability? So very briefly, of course, as a chemical group, we have, at least in Europe, to deal with the objectives that are set up by the Green Deal. And for Performance Polymer EMEA, for a compounding application, of course, we have already a lot of action that are on the way. First of all, we are producing locally, and this is also a kind of motto that we have globally. So we have a global solution, but we need to provide them locally. So it's one way also to find a way to reduce the carbon footprint of our material when we deliver them to our customer. Then we have already made a huge work in the last 2 years regarding the, the reduction of the consumption of energies in the factories. In France, for example, we have 2 factories and both of them are working 100% with green electricity. So many coming from hydraulic electricity. But it's already something we have implemented earlier on this year, 2024. And of course, this goes as well with a very close monitoring and reduction of the consumption of energy within the sites. I will start then with the fourth one here. So we are also developing a lot of tools that will help also on the eco design and measuring the impact evaluation of our solution. And typically, for example, we are developing also a competence center in Japan that will help us also to have to be able to propose to our customer on a very reactive way the LCA data of our materials. It's not only for performance polymer department, because we are already doing that with information we have already from the market and with a lot of verification today, because a lot of information are not always available yet, so it takes a lot of time still. But end of 2025, we'll be able to supply this service for LCA data. I will finish with the scope 3 because this is today the most impacting scope for materials. So we are dealing with plastic material that contain carbon. So all the story is here. This means that 70 to 80% of our carbon footprint is coming from our materials. So we need to find a way to make the material more circular and finding a way to replace the fossil and premium material by recycled material or bio-based material. This is the only kind of thing that will help on reducing the scope 3 of our material and the carbon footprint. So coming on the topic for today a bit more, so sustainability was one of the important things we consider, but if you look at the conductivity scale of materials today, we can go from insulative material to conductive material. So the first part of this presentation will deal with insulative material. We have material today that we have developed that are able to have a low loss for dielectrics. So this means they will bring a higher efficiency in the communication because they will be more transparent to electromagnetic waves and frequencies. So this will help on 5G applications. Second topic will be about more conductive material or dissipative material that have a low resistivity that can help to dissipate static charges, either making them also maybe conductive materials, and this would bring some possibility of having dissipative material and providing EMI, so electromagnetic insulation shielding. So starting first with the soft compound for 5G. First of all, you know that the frequency that our smartphones are using is always improving. So we started with 4G some years ago. Now we have a first generation of 5G that will be replaced by a new one, and maybe another one, and maybe coming to the 6G later. So the reason of this is that we have more and more use for sharing data and communication. So this means that we need to evolve the frequency to avoid that all the bands are getting saturated. So we need to go on higher frequencies. This will increase the communication speed and the capacity of data. But on the other hand, material also evolving, and we need to make this material evolving in order to make them more efficient. So also more conformable and helping us also to design new, to change the design and to make lighter material and maybe more conformable, more versatile materials at the end. So definitely there is a need for new materials in this area. Today there are a lot of rigid solutions, and one of our targets is to develop and to propose a soft material for this. Here on this slide here, you can see how the material, either rigid or soft, can behave in terms of dielectric loss. So dielectric loss means that once again the material will be either efficient or not in the communication, because it will be more or less transparent to the electromagnetic waves. So when we are on the low side, on the right side, this means that the material are very efficient. And today, most of the time, we are using rigid material like PTFE or ceramics. We are using also a bit of PET. So PET is not really soft, of course. It's more rigid, but we are able to. A lot of solutions are based on flexible PET film. So we use it. We consider PET to be flexible, not soft, but that's why it is also on this kind of graph. If we go on soft material, today we mainly recognize TPU and silicone being used for on the right side with having certain dielectric loss. So until a certain generation of 5G, in any case, at least for TPU, we know that the material can definitely be suitable for this application. But if we increase the frequency, we notice that TPU has some limitation. So our target here is to be able to bring more solution on the top right side. Why for? So this will be mainly for mobility, for example, LiDAR, so kind of radar system with light. A lot of application also in consumer mobility for Internet of Things, virtual reality, antenna, 5G covers for smartphones. And one application where you can recognize that the soft and stretchable material can be really beneficial in this case, it is also for healthcare. So our material can be supporting the development of this kind of application. How we developed this material, first of all, we have here a kind of circle we have made, iteration of studies that we have made in the last years, where we start with a TP formulation that we are validating on the process, that we are characterizing, consolidating the data and so on, and trying to improve formulation again and again. So the first step is really to make sure that the process is okay, because we have already a lot of companies that are producing material, resonators, material that are able to communicate, and we cannot change the processing. So we need to make sure that our material will still be good enough to perform with a standard processing. And typically we have been able with some partners to make soft TPE films that on which we can deposit some metal, that we can go on the curing system with UV, for example, and also on the chemical etching bath in order to make appear all the communication wires and so on the surface. So at the end, we can make a ring resonator that will be able to communicate and that we can characterize. So it's typically one thing that we have been able to show to demonstrate that our materials are able to pass this kind of processing steps. In terms of characterization, so we have just two examples here. So we cannot disclose formulation and confidential topics, of course. But for example, here we have tried to show you how we are dealing with polyolefins and fillers in our formulations. Typically, these ingredients have some impact. Not only them, but some of them have some impact. And you can see that we have been able, by selecting the right polyolefin or the right fillers, we have been able to decrease the tangent delta. So tangent delta will represent the dielectric loss, and by selecting the right ingredient, we have been able to maintain a certain level of performance on the high frequency. So here we are at 10 gigahertz, so 5G, 6G is starting in this way here. So in terms of materials, if we compare with commercial TPU that is already used on the market, mainly for 4G today and a bit of 5G, and also a rigid solution like PTFE, you can see that our material, soft TFA block, can mainly provide the ability to make more, to propose more ability to process. So having a stretchable material can help once again to replace some rigid material, but also to go on some innovative application by using the stretchability and elongation properties of the material. It is possible to see one sample on our booth, so I just recommend you maybe to see that. You will see a stretchable printed electronics. So it's really, we believe it will really help the ability to propose new kind of design for this kind of application. And you have been able to reach the dielectric loss that is today achieved with some rigid material. So ready to operate in this case. So as a conclusion on this slide, on this first part of the presentation, so on the technical side, on the left, first of all, low loss dielectric, low tangent delta means higher efficiency because the material will be non-transparent to all these waves and being more efficient, will capture more waves, and this will bring faster communications. Um, we have also a certain level of permittivity for material that is still in line. Value is 2.4 to 2.6 for people that are really specialists for this topic. I'm not, I'm sorry for that. But this means that this material with this kind of level of permittivity will be one kind of solution for supporting the miniaturization of components. Because of course we need to reduce the size of our components, and this need also to have a certain permittivity level. And last, we can also fine-tune some properties like flame retardancy, like thermal conductivity, and this will also help to increase the shelf life and the usage of the product. And on the right side, the other benefits of having a soft material, first of all, bringing elasticity and stretchability for this kind of application. The material is fully processable according to injection molding, extrusion molding, additive manufacturing also. And we have been also able to prove that it can have also an excellent adhesion on metallic parts and other kind of plastics and inks and so on. So we believe that this is kind of solution that would be really helpful to develop communication applications using the trend on the 5G and maybe 6G in the future. The next part of the presentation is more about conductive compounds. If we come back on this scale here, the idea is to focus more on the right side, because in general, this kind of property can help to dissipate static buildups, electricity buildup for safety reasons in the factories, to reduce also the interferences, and maybe in some cases so conduct electricity. So the idea from our side was to develop a soft Tefal with a low resistivity, below 10 to the power 8 ohm per centimeter, to still propose the colorability of our material that is always very good, to differentiate against black solution. And the reason, of course, is that we still see a lot of rubber that are black with carbon black, having very good performance in terms of conductivity, but that also limits the design. And last, being able also to propose circular options, meaning that we can use also circular material, bio-based material also for this kind of solution. So the potential market we can serve here, you probably know ATEX environment, where you need to make sure that you don't have a risk of any electrostatic buildup when you have a very fine powder or explosive powders and so on. So first of all, our kind of solution can serve in this kind of industrial environment. This can also be used for footwear application for the same reasons, because all the friction of the footwear on the ground and everywhere can create this kind of static buildup. Sports and leisure, do-it-yourself, tools and power tools, and of course plastronics in general. Starting with the standard ingredients, so we are using conventional polymers and plasticizer, some conventional adjuvants here that provide, let's say, standard properties, so quite insulative material and also quite rigid ones. So we have been able during this development to bring some solutions, some compounds in the range on the top right area here. So having a conductivity that would be a surface resistivity, that would be below 10 to the power 8. And trying to go as much as possible on the right side. But of course, 10 to the power 2 is kind of limit for us as of today. So why this was complex here? Of course, we have compounder, compounding, so we are mixing. It's a formulation and processing mixing. In this case, this kind of material have some specific properties. So we are doing the same kind of job, basically, but we are using some standard building blocks with very innovative one that can provide the conductive performances. So we made a very intensive screening of raw materials, studying the chemistry, looking at the miscibility in the lab with small bravenders and a lot of kind of thing like that, in order to make small, very small prototypes first and to check the data, what we can have and so on. Of course, we don't forget our scope is to propose a solution that can be easily customized. So typically providing circular compound, this is our logo here, circular, that's using recycled material or bio-based material, provides the ability for coloring, so we don't use black material. So sometimes we can have a bit of gray, a bit of brown, but in general material is not black, and this allows also to make some nice colors as well. And we worked a lot on the process, actually. I think a very big part is also on the processing, because we need to adapt the feed zones to make the right dispersion of our product, to work on the screw profile. And the idea here is really to make sure that we can create a connected network. So this is kind of thing that we need to achieve at the end, a colorable material in which the molecule would be connected all together. So I'm sorry again that you cannot see what is written behind my picture, but it will be a customized conductive network, and this is this network that will allow the charges to be dissipated in the plastic. So this is kind of plates that we have here. You can see them on the booth where we are achieving the surface solidity I mentioned earlier, that is lightweight, that is soft touch, colorable, sustainable as well, and that we can provide also with different kind of chemistries, meaning also different kind of polarities to our customers. And this will be my last slide today on opening what we can do now, or what we would like to do now. Just coming to the end of the time, and sorry for that for organizers. Of course, any idea of further collaboration is very welcome. We cannot work all alone here, so we really also would like to inform the audience today that we are willing to work in partnership on this. Because material processes are quite complex, are very specified, and we believe we should develop that with you all. So we know the next trend would be to work more on the 6G, to be working more on the EMI shielding as well. But it's kind of area of innovation that we need also to develop with you. So this is it for my presentation for today. You may have any questions, so I would like that you can maybe contact my colleague at the booth to address your question. We'll do our best to answer them as soon as possible. Once again, sorry for having this remote presentation, but I hope that it was clear enough, and that if you have any question, please revert to us. Thank you very much.